All right, so this is section 5.4. I wanted to start with some logarithm identities. So there's a lot to get used to, but we'll just have to practice individual ones one at a time. I put some things on the board that are every fact about logarithms is essentially a fact about exponential functions that's been turned inside out and backwards. So it's the same way as x squared is the inverse process of the square root. There, those are both just the reverses of each other. And sorry, it's crooked. Okay, now it's straight. Okay, anyways, what was I saying? So there's some exponential identities, and they're somehow connected to these logarithmic identities. I don't want to prove the log identities, but I do want to do some examples. So one way that you sort of get more comfortable with square roots is that you work with things that you know are perfect squares of whole numbers, and then it's easier to understand what's going on. And it's the same thing here. If you have a number and you know you can write it as 2 to the something, then taking log base 2 of 2 to the something, you just get the exponent. That's the whole goal of logarithms. I have a number that's in front of me. I want to think of it as what power of b am I looking at here? And if it's already written in that form, you get it immediately. So this just says that, how do you understand logarithms? Well, log base 3 of 81, well, that's not quite perfect, but if I write this as well, 3 times 3 is 9, so there's a total of, that's 9 times 9, so that's the inverse property. If I write log base 3 of 3 to the 4th, then the answer is 4. That's what logarithms do. And that's kind of the sort of starting point for all this. And because it's so that's just one example of this one. And then for this one, so if I have 3 to the log base 3 of 9, well, I'd better just get plain old 9, but let's see what we get. Well, this is 3 of log base 3 of 3 squared. So it should all be kind of the same here. So log base 3 of 3 squared. So either way, it just sort of all cancels. So it's nice if all the numbers in your problem are just powers of the base itself, and then everything you can just do by hand on paper, no sweat whatsoever. It's just kind of, you just sort of cancel the function with its inverse, and then you retrieve the exponent, and then that's the answer. That's nice when it happens. For everything else, there's calculators. So that's what I want to do here. So I'm going to make a little bit of room here. You can pause and take a look at this again if you want. But I want to start talking about some identities. So I just want to pick some nice numbers, and I want to at least do one example of each before we start doing problems that are sort of like book problems for the section. So eventually what we want to do is we want to get comfortable with simplifying longer expressions. And the ultimate goal is we want to solve algebra problems involving exponents, and then the logarithm is just a tool. It's like a thing that we can do to both sides of the equation at just the right step, and then things get things reduce down and simplify, and then we've got a thing that gives us our answer, just like a square root, but for exponential functions. So what have we got here? We've got this new thing, log base b of m to the p is p times log base b of m. And I claim that these identities basically correspond with each other basically, what power of b is this? Well, if it's m to the p, then it's p times as big as the exponent on just m itself. Well, okay, that's a bit of a tongue twister, but let's sort of write it down. So we've got, let's say that I want to take log base 2 of 8 to the 4th. Well, there's a couple of ways I could do this, but the identity says that I should just be able to put the 4 out in front. So let's sort of go off on the side and see, well, what is log base 2 of 8? Well, that's log base 2 of 2, 4, 8 is 2 cubed. Well, so the identity says that it says that I should just be able to do this. 4 times log base 2 of 8 okay, so 4 times log base 2 of 2 to the something is you just get the exponent. That's the whole idea of a function and its inverse. And we should be getting 12. So log base 2 of 8 to the 4th should be 12. Well, let's see if we actually get that. So let's sort of think about it from a different perspective. Let's just do... What I want to do is I want to think about the same problem. I want to solve the same problem, but I want to think about it from the exponential identity point of view, just to sort of show that these ideas are connected to each other. So we've got 2 cubed to the 4th power is what we're taking log base 2 of. So I'm taking log base 2 of 2 to the, well, that's 3 times 4 is 12. And log base 2 of 2 to the 12th, that's the inverse. You take the inverse, you do the inverse property. So what did we do? We multiplied, this 12 came exactly because we multiplied 3 times 4. So we solved the exact same problem 2 different ways. One way, we use the exponential identity, and then use the logarithm to just cancel the bases. And the other way is we use the logarithm identity to just sort of do everything in terms of logarithms. And this is the kind of example that anytime you want to convince yourself that you really understand these things and that they really work the way that you think that they work, well, you don't try to take the square root of 12 in your head, because that's hard. But you want to pick whatever your function is. You want to pick numbers that are nice for that function, and then if that's what you're messing with, then you'll understand it a lot more immediately. It's a lot easier to understand this one because I used 2 to the 3rd, 2 to the 3rd to the 4th power. And that's a model of how it works with every positive base and every positive m. It's that this model, the same thing just works because the same identities, the same backbone is sort of running through every variant of this problem you might encounter. So just, I could have used 5 squared in log base 5. Anything, it would have worked out kind of the same way. So that's sort of explaining, it's not a proof of the identity, but it's an illustration. It says that something exactly like this is going to happen for every base, no matter, in every exponent. That's just a perfect illustration of what always happens. And so want to look at this next one. Well, let's sort of understand why this one is true. So let's say I want to take log base 3 of 9 times 27. Sure, let's do that. let's do it kind of the old-fashioned way. Let's say, well, I'm a lot more comfortable with exponents. So that's a 3 squared, and that's a 3 to the third. And this is completely correct. This is 3 to the fifth. Log base 3 of 3 to the fifth is 5. So great. So yeah, if everything were a power of 3, our life would be easy, because we don't, we can sort of, we can just simplify everything and cancel everything out, and it just works. And we didn't have to know what the identity was or how it works or anything. So, but usually our life is a little bit more complicated than that, because the numbers aren't very nice. There could be variables, positive variables. And we still need to be able to use this brand new identity. So this is kind of using the exponential identity. But what did we do? We took that exponent and that exponent, and we added them. So we just log of the product, we added the logs, we added the exponent. So log, what is the exponent if you think of that as a power of b, or in this case, a power of 3? So that's the exponential solution kind of thing. Well, we have to learn the log one, because usually we can't just look at it and say, oh, there it is, that's 3 squared and that's 3 cubed. Our life is easy. Usually you can't do that. Usually m and n are just some other completely unrelated numbers, like 25 or something like that. But we can still do it. So here's what you would have to do in general. Log base 3 of a product. Well, the brand new identity says that instead of manipulating the product, we just apply the brand new identity. We just add the logarithms. And if it so happens that those individual numbers are really nice, then we'll get the same thing, but we go about it in a different direction. So it's kind of like with these when you have different identities that approach the same thing from a different angle, it's kind of like crossing the street twice. You need to get to the opposite corner of an intersection, and it's like, you cross one street and then the other, or you do the opposite, and then they both get you there. So sometimes that's just how it is. Other times one way is kind of, sometimes there's only one way to do it, because you're limited in what options are available. And we'll see that soon. Yeah, and then the only thing I want to, let's do one with fractions as well. So yeah, why not? So still kind of just sort of the basics, getting used to the idea. Log base 5 of 25 over 125. Well, that's 5, that's log base 5. I have enough room, I can write it bigger than that. So there we go. Log base 5 of 5 squared divided by 5 cubed. Well, if I'm dividing two different powers of 5, then I subtract the exponents. So you end up getting log 5 of 5 to a power. That exponent is -1. That's sort of the exponential identity solution. Now the log identity solution of the same problem is let's sort of just break the problem down, but in a different order. Yeah, so that's 5 squared. Yes, so this boils down to, this is actually 5 cubed. and that's a 2, and then that's a minus, and that's a 3. This minus is from this formula because we're taking the log of division, and we get -1 once again. All right, so before I go on, I want you should almost everything that's really important about logarithms has basically already been written on this board somewhere, and anything involving something else is just there are these fake identities that are just nothing. It's just you can't do anything with like log base 5 of x plus y is just nothing. It's just whatever that is. You just, what x is a number, y is some number, log base 5 is some complicated thing you have to do with your calculator. There is no relationship between log 5 of y and log 5 of x. It's like nice and straightforward. There's just, you don't get anything for free out of that. There are no identities where there's a plus on the inside of the logarithm. So there's nothing fancy. There's nothing good about this. It's, if it comes up, then it just is what it is, and you can't really simplify it. It's just, that's what it is. And some things you can simplify or turn into other things that might be useful. Other things you can't. And this one is just this and a few other ones. They're just some very, very common mistakes. But what I just did is I did these 3 identities which are true, and I showed you examples of how do you do a numerical experiment to convince yourself that these work the way that they say that they do. And you'll sort of get that. Because of things like this. Yeah, so the only other thing, I didn't say anything about this, but log base b of 1 is 0. And the reason for that is if we take log base b of both sides of b to the 0 is 1, which means that this left-hand side is b to the 0 is 1. So if I take log to the base b of both sides, the left-hand side is a function and its inverse applied to 0. And it just and that just is what it is. So sometimes that comes up as like, it's an important reference point to have in mind as well. Let's start doing some of these. Change of base formula, I put it on here as well. It's an important one, but we already, in section 5.2, we already used that and applied it to some problems. It's a nice one. Right now it's not the emphasis, but it is something that we have seen, and maybe you'll see it again. Okay, so So one thing about logarithms is we want to keep in mind that there are domain issues. We want to the logarithm has to assume that the input is a positive number, or else lots of contradictions and false solutions can pop up here and there. So we're just to be mindful of that. So there's a couple steps. So notice that there's this, we have these constants in front. And there were some identities on the other side, and kind of whatever the base is, you just use the same base for the whole thing. And kind of there's a generalized version of all this, and it boils down to just applying the identity multiple times. And I just wanted to tell you just what the end result is, because it's, well, however many things you have, what ends up happening is you just get pluses for all the things in the numerator. If it's a product divided by another product, you get pluses for all the things in the numerator. And this general pattern works for however many you have. So in this case, I'm saying this because the identity that I gave you only tells you what to do with two terms divided by each other, or two minuses. But if there's three minuses, then it's like this. So you subtract. So if it's inside of the logarithm and it's a fraction, then the factors of the numerator are added as, log of a plus log of b plus log of c plus log of d, and then the factors in the denominator, you subtract those logarithms. So it's log of this plus log of this plus log of this plus log of this, but then it's minus log of this minus log of this minus log of this. And it just that's just kind of the way it works out. It's a shortcut. It's kind of, if you were to do it one step at a time, well, the reason is basically because, like, if you have multiple things in the denominator, another way of looking at it would have been, well, that's just log of one thing minus the log of, so if that's m and that's n, then I break it down once and it looks like that. But then it's just really annoying. It's like, it's better to show you the general pattern. But if you were to use just those first two identities over and over again, eventually you would get to this general result. Because what happens? Well, if I want to do it just one step at a time, it's like I need a capital M and a capital N. And okay, so I get this stuff, and then I can still break it down further. So it's like, well, maybe now capital M is these three terms. So ln of ABC plus ln of D. So this one, if the first three is capital M and the second one is capital N, and I just do one step, it goes like that, and it's kind of silly. And then I do the same thing with this one, and then there's this minus on the outside. Eventually, I get a minus, and then we have ln of x plus ln of y. If I do it one more time, it gets, and then I distribute the minus. That's what you get. Okay, so It's just, yeah, the textbook says, the textbook says that's how you do this, but then that formula doesn't say what do you do if there are three things. Oh no. Well, if there are three things in the numerator or four things in the denominator, the pattern looks like this. It's hard to write down one formula that says every single thing that could possibly happen. I guess that's what examples are for. But what happens? Well, this one we can't combine them just yet because we have these constants on the outside. So 4 natural log of y, as I could write it this way, ln y to the fourth, and then minus, I'll just keep that one the same for now. So I've got ln, and the thing is I can only have plus or minus ones on the outside. And then that's the only one that's a plus. The other ones, if I'm subtracting the natural log of y to the fourth, and I'm subtracting a log of z, then z is a factor of the denominator, and then that's it. That's probably the simplest way to go about it. It's just how do you combine logarithms? Well, they better have the same base, or else these have nothing to do with each other. If all your logarithms have the same base and you're just adding and subtracting constants times log of something, you put the exponent, or the multiple on the outside becomes an exponent on the inside. So you put it inside as an exponent. And once your exponents are all on the inside, then you multiply by the pluses and you divide by the minuses, and that's really all there is to those. What else? Sometimes we do the opposite. We ask you to expand things. Okay, so something like that. So this is just plain old log, which you should remember that if they don't specify a base, that has to mean log base 10. And that means you have pluses for the numerator factors. Well, it has to be times. So if it's on the inside, if it's plus, then that's just, you can't do anything with it. But on the inside, it's times. So you take the factors, you add log of the numerator factors added together, so log of 100 plus log of x cubed, but then minus log square root of y times square root of z. So it's log of square root of y and log of square root of z, however you want to. Yeah, those two are kind of similar to each other, but this is log base 10 of 10 squared plus 3 log of x minus, this is log of y to the 1/2 minus log of z to the 1/2. So we get 2 plus 3 log of x minus 1/2 log of y minus 1/2 log of z. All right, let me take another look real quick. I think I covered just about one of everything, but there could have been, just want to see if there's any more curveballs I forgot to include. Okay, yeah, okay, ones with little polynomials. So that's Not too bad. I'll do one of those though. So this is just being a little bit cute or clever or whatever. It's just take two things that something that you just learned and something you already learned, put them together, and then just sort of put it all together, and it just works. So let's do something like that. So log base 3 of x minus 1 plus log base 3 of x plus 1. Let's put twice that. I don't know. Maybe 3 of these, and then minus twice log base 3 of x squared minus 1. All right, just, I don't know. This one's a little bit silly, but it's, I don't know. There's nothing wrong with it. So this is x plus 1 is an entire self-contained quantity that we're taking the logarithm of, so that whole thing is squared. So this is the thing that you're applying the function to is like a whole entire, it has like implied parentheses, it's a whole, that entire quantity is the input of the function, so make sure you group it with parentheses when you do this kind of step. X squared minus 1 squared, okay. So what do we have? We have x minus 1 cubed times x plus 1 squared. Everything has log base 3. So we add these two logs, so that's in the numerator. And then into the denominator, we have x squared minus 1 squared. So we can actually do a little bit. We can mess with this just a little bit. So this is x, if we had a single x plus 1 and an x minus 1, then that actually is equal to x squared minus 1. So let's... Well, let's take the one in the bottom and let's just sort of... That's right, let's think of it that way. Okay, because what do we have? We have x plus 1 times x minus 1. The one in the denominator is this. So that thing in the denominator, yeah, this will be the easier way of thinking about it. So we expand that. Now we have a lot of common factors. So these cancel completely, and we have just one of these left over. For this section, this is all you have to do. There's something I want you to keep in mind. So again, I can't talk and write at the same time or else I mess myself up. So I just want you, it's just so important that I'm going to say it right now, but we're going to deal with this in detail in 5.5, but as a preview, and I want you to have the right idea as early as possible. If instead of just simplifying one expression, if you have two expressions that are set equal to each other and you have to solve for x or whatever, you do all these manipulations, you might be like canceling two negatives. So sometimes the final expression is well defined, but the original expression was not well defined. So you get those extraneous solutions that it's like you did a perfectly good method. It's just that some of the solutions actually work and some of them you throw out, and you found everything that could possibly be a solution. It's just some of them are false, but whatever's left over are the only solutions you were ever going to find. This is an issue that's going to come up shortly, because whenever you do simplifications, you combine logarithms. If you take a log of a negative plus a log of a negative and you combine them, then nonsense plus nonsense is suddenly log of a positive number, which should be kind of illegal in hindsight, but that's, you just kind of assume that everything is positive and everything works, and then check your answer at the very end is how you make sure you don't run into anything too dangerous. So just keep that in mind. In this case, we had to assume x minus 1 is bigger than 0. We need x plus 1 bigger than 0. Like, these are the assumptions we needed to even begin talking about this expression here. And that's a sort of a hidden assumption. It's easy. It's a technicality. It's easy to forget, but technically, it's vital and important. Just when we get to 5.4, we'll see that. But yeah, that was a lot. I hope that helps. You might watch that a couple times. It takes some practice. There's some book problems. The examples in the book are pretty straightforward. You get, if you just skim the chapter and you look at all the simplification steps that they do, you'll get, by repetition, you'll get a better feel for the big picture. So yeah, you'll want to go ahead and do that.